Okay, so I said I was going to record a video talking about Laplace domain circuits. So that's what I'm going to do. The way that I'm going to structure this is you can feel free to pause the video anytime to copy down the diagrams. I'm going to need to kind of modify the diagrams. I'm going to generally do that while I pause the recording so you don't have to listen to me clicking quite so much, clicking the mouse. But this is the particular problem we're going to work on. So I wanted to modify the Fourier domain example that we were looking at in class into one that is appropriate for a Laplace domain analysis. And this first slide shows a couple of important bookkeeping or record keeping details that we need to keep track of when we're using a Laplace transform to solve the differential equation here. Okay, and so on these diagrams, I forgot to list that we're going to measure our V out across the LC tank again. And see what the differential equation looks like in this situation. But I'll draw that annotation in a little bit. All right, well, I figured I'd just throw it on here anyway before we continue. Okay, so the goal of this problem, which is probably good for me to mention up front, is we're going to calculate V out of t under the conditions that are specified up in the top left here. And up here, I drew the problem I wanted to construct in a switch-based form. And so because of the way this switch is described, and actually, we usually put the little circles on there. So this switch up in the top left, at time t equals 0, makes a clean move from 6 volts from connecting a 6-volt source up to the resistor, inductor, capacitor before the switch moves. And then after the switch moves, we're connecting a 12-volt source to this resistor, capacitor, and inductor. Okay, and so this transient, the switch flip, is going to create a different stable set of conditions that this circuit operates under. Um, and we'll actually see what happens as a function of time after the flip of the switch, but it creates a disturbance in the system that necessitates the various parameters, the various network parameters to change, and so it does so according to the differential equation that we would have to write down if we weren't going to do this purely in the Laplace domain. So in the switch form, this is kind of the situation we were in the first or second order earlier in the term, but it can be kind of tricky sometimes to get from the switch form to I guess it's not really that tricky, but it can be, especially early on, to convert this from a switch form to a more standard, purely differential equation Laplace transform style of this. So you'll see a lot of problems that start out written the way I have here on the right, just because it's a lot easier to keep track of and know exactly what you're doing. So I specifically chose my problem on the left side so that it would very naturally than it sometimes does at least. This is one of the most natural ways to have it very clearly map onto a particular circuit structure. Okay, so we start at 6 volts, and at time 0, the voltage suddenly jumps to 12 volts. So that can be expressed as a constant 6 for all time, plus 6 times a step function, and the unit step, u of t, the Heaviside step function, suddenly goes to 1 at time 0. And then because there's a 6 out front, 6 plus 6 u of t starts at 6 from time t less than 0. And then after time t is greater than or equal to 0, it makes a sudden jump up to 12. And that's exactly what we're dealing with here. Now, something that I feel like I need to clarify up front, because you'll kind of see this getting skipped over a little bit, is when we convert to the S domain, to the Laplace domain, there is not going to be a distinction in terms of what is the Laplace transform of 6 plus 6u of t? It actually has the same Laplace transform as 12u of t. So what's important to remember is that I have written this very carefully to be an accurate description of this circuit for all time. This picture is not really accurate to what is going on in the original picture. Now, when we go to solve this, the source itself will look exactly the same. When I take the Laplace transform of 6 plus 6u of t, I get 12 over s. And if I do the same thing to 12u of t, I am also going to get 12 over s. And the reason for that is in the Laplace domain here, when we're doing differential equations stuff, we use the single-sided Laplace transform. So we are actually only going to integrate this function times e to the minus st from 0 to infinity. From 0 to infinity, there is no difference between 12u of t and 6 plus 6u of t. It has the same value at every point for time t 0 or larger. So when we integrate from 0 to infinity, even times e to the minus st, it makes no difference. We are allowed to use the single-sided Laplace transform because what we are going to do is be in a situation where all of the information about past values of t is all going to get wrapped up in the initial conditions. So we use the single-sided Laplace transform in combination with the initial conditions to cover all of time. Now, if it matters to us what is happening, or if things aren't so simple for time t less than 0, then we might have to be a little bit more careful. But in the particular problem we're dealing with, we're assuming that the switch has sat in its original position for a long time before it moves. And so any transients from the past are long gone, and we can just assume that if this switch has sat open for a long time, we then can determine the initial conditions of the circuit. The initial conditions will take the form of the initial capacitor voltage and initial inductor current. So the difference between 6 plus 6u of t and 12u of t, it is going to still transform to 12 over s, and we're going to replace this source and say that it is a 12 over s source in the s domain. The difference is 6 plus 6u of t implies a different set of initial conditions than 12u of t does. So when we go to the s domain, the source will look the same, the capacitor and inductor will not between these two calculations. Okay. So in reality, I'm going to use the first picture to take the Laplace transform. And so the way to resolve this is that if you use when you look at a table of Laplace transforms, some Laplace transform tables will tell you that the Laplace transform of 1 is 1 over s. And some Laplace transform tables will only tell you that the Laplace transform of u of t is 1 over s. If we are using the one-sided Laplace transform, both of those things are true. The Laplace transform of 1 is 1 over s, and the Laplace transform of u of t is 1 over s if we are using the single-sided Laplace transform where only the values for t greater than 0 are going to matter. And on that interval, those two functions, 1 and u of t, are indistinguishable. If you are using the two-sided Laplace transform, the two-sided Laplace transform of u of t is 1 over s. The two-sided Laplace transform of 1 is not 1 over s. And that's only sometimes an important distinction to make if you are doing the two-sided Laplace transform. So you'll see tables that are referring to the one-sided Laplace transform, and then they don't have to distinguish between 1 and u of t if you're doing that. Um, and so I hope it's kind of long-winded of a discussion, but I really wanted to point it out up front because it matters. These details are important. They get run right over and kind of hand waved away, but they're still important. We just write the problems so that we don't need to worry about them, and so they often don't get mentioned, even though they do matter. Maybe I'm just being a nitpicky signals guy, but I'm pretty sure I'm in the right on this. If you ask a mathematician, they'll agree with me. I assume the physicists would too, but who knows? Anyway, so I'm going to use the first picture. And so we're going to get 12 over s here either way, but all right, so I've got my slides here. So the thing that we're going to do now is we need to convert each circuit element into the Laplace domain. So this is going to be the portion where the values of this, where the value of the source for time t less than 0 is going to matter, not in the resistor, but in the inductor and capacitor. In the case of a resistor, it can't store any energy, and so its initial conditions don't matter. They're allowed to just move freely. It's the initial conditions of the inductor and capacitor that matter. So the circuit element or the element for a resistor in the S domain, just like in the omega frequency domain, a resistor just gets replaced with a resistor whose value is still R. It looks the same under a Laplace transform because a resistor is just an element that has a fixed ratio between its voltage and current and time. And so then when you take the Laplace transforms of V equals IR, just by linearity, you just transform V and transform I, and it doesn't change the calculation. You transform both sides and you just get R as a relational coefficient there. So you just let resistors keep their value, but it is the capacitor and inductor where things get semi-interesting here. I guess I should full screen this. That looks a little better. So for a capacitor, if we label V of t and I of t, then there is an initial capacitor voltage, V of 0, that exists on this capacitor. So at time 0, when the transient move occurs, we know the voltage on the capacitor. Whatever that is, we call it V of 0. And then the capacitor becomes 1 over SC, which is what we would expect. It's just like 1 over j omega c. But then the initial voltage on the capacitor becomes an independent source in the S domain. And so this comes from the fact that in the capacitor, the current is proportional to the derivative of the voltage. And so when you take the Laplace transform of a derivative, you get S f of s minus the initial value f of 0. So this same thing happens for I in terms of V. And so we end up with this V of 0 that acts as a source. Now, the exact value of the source depends on which source type we choose. And we choose a particular source type to go with a particular equation, a particular version of the equation. So if we solve for I of s, we get V of s over 1 over SC. So the 1 over SC is the impedance looking portion. But then it's minus C V of 0. And so when you do that, CV of 0 becomes a current source, which faces in the opposite direction of the passive current going in, which we don't really need to worry about keeping track of that. What matters is that the initial voltage is positive on top here and negative on the bottom. So either we draw a current source or a voltage source, either way, that source is consistent with a voltage that is high above and low below. So the current source goes from low to high, and the voltage source has its plus minus matching. So this is the matching source configuration in source transformation. And so it shouldn't really be too surprising that if you take a parallel current source and impedance, that's equivalent to a series voltage source and impedance just by source transformation. And algebraically, rearranging the equations leads us to that conclusion as well. So there's a little bit of semi-finicky math here, but the ultimate result is you can either draw the S-domain version of a capacitor in a series configuration or in a parallel configuration. It will not change your answer. However, one may be easier to deal with when placed in the circuit than another. So that's really the only reason you use one versus another. Whichever one makes your analysis more convenient is the one you want to drop in. But you can drop either one in and it is still possible to analyze nodal loop. You can do the source transformation after. You can do Thevenin's theorem, Norton's theorem. Once you're in the S domain, all of the same techniques are available. So you can find a Thevenin equivalent circuit using all of the sources and impedances that appear in the S domain. Okay, so it's up to you which way you want to do it. You just have to make sure that the polarity matches. So the polarity matches with the initial polarity of the voltage. So you define the initial voltage, give it a number, and so to give it a number, you have to define a polarity. Once the polarity is set, then the polarity of the S domain is set in comparison to the time domain polarity of finding the initial value. All right. Okay, so we can drop either of these into our circuit, and one of them is going to be easier than the other. I guess they're probably both pretty easy. So you simplify the capacitor down, and so it's just 1 over SC, either in parallel with a C V of 0 current source, or in series with a V of 0 divided by S voltage source. Okay, this makes some sense. So V of 0 is a lot like a constant, and so the Laplace transform of a constant is the constant over S, because the Laplace transform, or at least the single-sided Laplace transform of 1 is 1 over S, so the single-sided Laplace transform of the constant V of 0 is V of 0 over S. So when it's written as a voltage, it's V of 0 over S, of course. In current form, it's coming from, C dV dt, and so there's a C V of 0 as a result of its calculation. So it matters which one you're using to determine which of these two expressions needs to go into place. That's the other thing to keep track of. A similar analysis with the inductor, because this one is current-based instead of voltage-based, it's the passive direction of the current that matters. So if you define I of 0 and you calculate and give I of 0 a number based on a polarity from top to bottom, then when you use the parallel current source, the current source points the same direction as the initial current. And so the series voltage source has the polarity that matches with that current source under source transformation. It's always the way I think about it. So if you're doing inductors, you're doing current, you're dealing with the initial value of current. If you're going to draw it current way, put the current the same way, in the same direction. And I think of that first, and then that reminds me what the voltage has to be. But you also have to remember, and then I remember, okay, the current is constant, so it's I O over S. And so I know and then I just remember the other one must be L I of 0 pointing in the matching polarity. Or you can just always have it in front of you. You don't have to memorize it, but you could. That's the way I tend to do it. I say that as though I don't look it up every time. I do. I could probably remind myself, I could remember it, but I feel better looking it up every time. So I absolutely do that. It's completely fine to look it up every time. If you had to, though, you can probably piece it together. You just kind of have to really think it through a little bit. But you can always just look it up, and that's fine. So we get either the series model or the parallel model, and we just place whichever one is appropriate for the circuit that we're dealing with. Okay, returning to my slideshow. I'm about to convert this to the S domain, so I erased everything. I wanted to, because we weren't going to use the values it had, so I just erased everything for the ones on the right. I'll modify it again in a moment, because what I need to deal with right now is this other circuit that I've drawn here on the left. So this was the part I erased, the piece of, you could probably see that, but that's what I was referring to. I didn't have the pointer on. So in order to determine the initial conditions required by the S domain, I need to look at the circuit for time t less than 0. So in this circuit, that's a 6-volt source. I can obtain that either from the switch or from the 6 plus 6 u of t version. Okay, the 6 is this 6 or this 6. Either way, we get 6 volts. We have our 100 ohm resistor, and in the long run, if the switch has sat in its original position for a long time, the capacitor begins to act like an open, and the inductor acts like a short. So I've drawn that in here. And our initial conditions are calculatable in this configuration after it's been allowed to sit for a long time. So we know a couple of things right away. One is that this capacitor voltage, because this is open, we know that no current can be flowing through the capacitor's path because it's open, and therefore all of the current is passing through the inductor's path, which is a short. So that works just fine. So all of the current in this circuit is passing through this outer loop and no current in here. But since the inductor's path is short, this is just a single loop containing a 6-volt source and a 100 ohm resistor. So therefore, Ohm's law tells us that IL of 0 must be 6 volts. 6 volts divided by 100 ohms. 6 volts divided by 100 ohms is 60 milliamps, not 6. Okay, so we had our initial, which I knew. I calculated that when I wrote the problem, and then I kind of lost track of it when I was getting ready to record it here. So we get that IL of 0 must be 60 MA because of the short path. We also know that because the inductor provides a short path, there cannot be any voltage drop across a short. And so that also tells us that VC of 0 must then be 0 volts because of the inductor creating a short that doesn't allow any voltage drop. Okay, so in the original position, after a long time, this resistor allows a current of 60 MA, all of which flows through the inductor after the capacitor has completely discharged because of the inductor discharging that capacitor down to 0 by acting like a short. So these are our initial conditions. So I might kind of run these clicking now. So for time t greater than 0, which is where we're going to apply our Laplace transform, the Laplace transform of 6 plus 6 u of t we know to be 12 over s. We know our resistor takes the form of a simple 100. Now, the thing that is going to be different now, I'm actually probably going to want to slide this inductor over to give us a little bit more space. Because these two elements are already in parallel, I'm going to use the parallel version of these elements. So in a capacitor, we know that the source that the capacitor tries to generate is parallel with the capacitor, and the initial capacitor voltage is plus to minus. So the initial capacitor voltage source points up. In this case, it doesn't matter because the value of this is going to be C times VC, but VC is 0. And so C times VC is a 0 ampere. I guess it would be microamperes when we multiply volts by microfarads. But 0 microfarad volts are 0 microamps or 0 amps. And so the source that the capacitor produces as its initial condition has a value of 0. And a current source with 0 amperes of current is trying to tell us that no current flows through this 0 ampere source. Well, a 0 ampere source, if no current is flowing, it's indistinguishable from an open. And so while we could write this as a 0 ampere source, it makes more circuit sense to actually say that this is just an open circuit. And so then we don't even have to draw it, actually, but the inductor has a non-zero initial condition, and we're also going to use the parallel configuration for it. Okay, and then I just realized I got distracted. So the capacitor is 1 over SC. So off to the side here, if I calculate 1 over SC, well, I know that C is 1 microfarad. So this capacitor then generates, an impedance in the S domain. It's 1 over SC. If C is 10 to the minus 6, this is 10 to the 6th over S. The inductor is SL. L is 1 Henry, so this inductor is just S. The capacitor's initial condition is 0, so it provides an open circuit. If we had used the series, you would get a voltage source whose value is 0 over S. A voltage source of 0 acts like a short. So that voltage source would be series with this capacitor, but then it would act like a short, so then we would replace that voltage source with a short, and it would just also look like this. When we do the parallel one, we then have the option of drawing in the open for a current source of 0, but this is the same thing. And then the initial value on the inductor was 60 MA. Our slide tells us that we write I of 0 over S for this source when it's written in parallel. Okay, and so then this is 12 over S. We just want to remember our scale. So this is volts, and then the 60 over S is milli. So it would probably be cleaner to say this is like 0.06 over S. If we want to drop our units, we would write this as 12 over S and 0.06 over S, and then it would be really easy. In fact, I think that's what I'm going to do, just so that everything's in base units, or the basic form of the units. This is just going to be 0.06 over S and 12 over S, and then I don't really need to write down ohms or volts or amperes. We're fine. Okay, so this is the S domain circuit, and we've done all of the important Laplace transform steps up front. We've transformed every element one at a time into the S domain. And from here, it's just a regular KVL, KCL. These are all now impedances in the S domain and independent sources. So you just analyze it like a DC circuit, except that there's a variable S running around. But this is not too bad, so it just becomes a matter of writing down this equation, which I will do right now. Oh, but not before I note that this is the V out of S that we're looking for, because V out of T was here. Now after the Laplace transform, V out of S is here. And all we need to do is calculate V out of S and then invert the transform. So writing down our equations, we can just apply a nodal analysis here, if that's what we want to do. Or we can do a source transformation. You can parallel these two impedances, and then you could then turn this into a series combination, but I'm just going to push through it with a nodal analysis. So the current running to the left here is V out of S minus 12 over S divided by 100. Okay, then I'm just going to say that this is equal to the sum of all three currents going down. So this one's going, or I guess these are all going out of the node, aren't they? Okay, so I'm just going to say plus then, never mind. At the end, I'm going to add this up, and this is going to be equal to 0. Okay, so we take V out minus 12 over S over 100 plus, okay, this is V out of S over, let's just write it as 1 over 10 to the minus 6. Just making this a pain. Okay, so this is V out of S. V out of S divided by, okay, so this is 10 to the 6 over S. That's fine. Plus V out of S over S. That's the current through the inductor. Plus 0.06 over S. And that 0.06 is just a number of amperes divided by S. Okay, so we get this calculation. Now it's going to be a matter of moving the V outs to one side and then everything else to the other. So that's going to be fine. If I do that, we're going to have to, okay, I'm going to leave the V outs where they are. So this is going to be V out of S over 100 plus, this is going to be S over 10 to the 6th. V out of S, that's a little bit cleaner. And then this is plus V out of S over S. Whatever happened there. And so then those are the V outs, and they're going to stay on one side. And then I'm going to move the 12 over S over 100 and the 0.06 over S to the other side. Okay, and so then that's going to equal 12 over 100S is like 0.12 over S minus 0.06 over S. Combine those together, and this is just going to be 0.06 over S. Which already says something very important, that 0.06 over S is the 6-volt difference from 6 up to 12 divided by S. So the initial conditions are what, again, are compensating and ensuring that this actually does what it should do when it starts at 6 and goes to 12. The part where it started at 6 is incorporated into the S domain in a really elegant way. And so it ends up not appearing in this version of the equation, or at least the second version of the equation here, after just a small amount of algebra. Okay, so we now need to factor out v out of s and then divide by whatever is going on over here. So we know that v out of s has to be 0.06 over s divided by 1 over 100 plus s over 10 to the 6 plus 1 over s. So that's pretty good. We probably want to multiply the numerator and denominator by 10 to the 6th, or 10 to the 6th s, actually. So if I multiply this by 10 to the 6th s, yeah, then we're going to get 1, 2, 3, 4. So this is going to be 6, 0, 0, 0, 0. And then I'm multiplying by s as well as 10 to the 6th. This is going to be 60,000 divided by, okay, 10 to the 6th s here. Well, actually, we'll start here. So 10 to the 6th s is going to give us s squared. Then the 1 over 100 is going to give us 10 to the 4th s. And then the 1 over s is going to give us plus 10 to the 6th. Okay, so that's pretty good. This is somewhat almost factorable. And so this is approximately 60,000 over s plus 101 times s plus, whoa, what? I took a nap today, so I don't know. I took a nap for like 3 hours. I was so tired this morning. But I just had dinner, so maybe I'm starting to lose it. Okay, so it's approximately factorable in this way. Okay. So the only thing remaining to do is to invert the transform for v out of s. Man, this video is going pretty long. We're almost there. So from here, you could punch this into Wolfram Alpha and ask it to invert the transform for you. That's one way to do it. Or at least show you the partial fraction decomposition, which it will also happily do. But I'm going to focus for the rest of the video here on um, the sort of the three main ways to try to set this up to deal with the partial fractions. So I'm going to have to clear some stuff out, and then we will deal with this expression. So at this point, we set up our partial fractions, and so this is approximately equal to a over s plus 101 plus b over s plus 9899. Okay. Because we're approximating, this isn't going to work exactly, but it's going to be close enough that we kind of have a number of different options to deal with this. So one option is to multiply both sides of this expression by the denominator and solve the system of equations. And so that's not too tricky. If we multiply by the denominator, you're going to get a situation where 60,000 must then be equal to a times s plus 9899. plus b. So I'm just multiplying both sides by the denominator and then canceling the factors that are common. And then we'll get s plus 101. And if you multiply this out, you get two equations that tell us the s's have to match. There's no s on the left side. So we can say, well, that means that 0 must equal a plus b, because it's as plus bs. And then our second equation is the one that says that we know then that if we compare the constants, that 60,000 must be equal to A times 9899 plus B times 101. And this is a perfectly solvable system of equations. That'll work just fine. So this is the one that takes advantage directly of the fact that this needs to be true for all s. Mathematicians have told us it will be true for all s as long as this is an accurate factor. And if the factors are close, then this will be approximately true still. And so you can do this. Another approach is to just plug in some nice values of s directly. So if you just didn't do any multiplication on both sides and you just said, yeah, I'll just plug in s equals 100 and s equals 9,900. And you'd plug in those s values and you'd calculate what the left-hand side is, and you'd calculate, when you plug in 100, you'll get a over 1 plus b over, you'd have to put it, sorry, you'd make s negative 100 so that you're dividing by 1. And then you'd make s negative 9,900. Yeah. And one of your equations would look like a over 1, and the other equation would give you b over negative 1. And you'd punch your way through it. Some other nice numbers are like s equals 0, and then your denominator just, this side would just become 0.06, and this side would be a over 101 plus b over 9899. You can pick any two s's, and you'll get a system of equations that's just as good as this one. So that'll work too if you just pick two other s's. Or you can solve the system of equations from directly comparing the coefficients. Although the one that is generally preferred is the one where we multiply only one of these out and then get a different system of equations. So there's another method that allows us to calculate a and b directly. And so that's the one where you multiply both sides by just one of the terms and then plug in the s value that makes it 0. So if I take both sides here and I multiply by s plus 101, the left-hand side here becomes 60,000 divided by, if I multiply by s plus 101, what's left of the denominator is s plus 9899. And then on the other side, after I multiply by s plus 101, all that's left is a, whereas the b coefficient is then b times s plus 101 divided by s plus 9899. And again, this needs to hold for all s. But now, if I plug in s equals negative 101, s plus 101 becomes 0 times b over 97, 98, or yeah, 97, 98. The numerator is 0, so b vanishes. So then if we plug in minus 101 for s, that tells us directly that, again, it's only approximate because the factoring was approximate. But we know then that if we plug in minus 101, a is approximately equal to 60,000 over 9,798. And we can calculate what that is. Okay. And if you do the same kind of move after you multiply by s plus 9899, it's going to tell you that b is approximately equal to 60,000 divided by negative 9,798 and must thus be approximately negative 6.124. Though the equation over here that says 0 equals a plus b tells us the same thing. And so does this one that's a function of a. If you multiply, this equation in a also tells us the same sort of thing, doesn't it? Oh yeah, but it's just not written as conveniently. Yeah. Yep. So those are our coefficients. So that tells us then that V out of S is approximately 6.124 over S plus 101 minus 6.124 over S plus 9899. Invert that Laplace transform, and that tells us that V out of t, and I have some commentary about what this implies about the circuit. We can actually make some physical sense of what's happening. So our V out of t must then be approximately 6.124 e to the minus 101 t minus 6.124 e to the minus 9,899 t, as long as t is greater than 0. So that's the answer. That's technically where the problem ends. And so you can end the video right now if you want to. The only other thing I want to note is that this answer makes physical sense, actually. So in our original circuit up there, we started at a 6-volt source, and we calculated then that the current in the inductor was 60 milliamps right before the switch flips. Immediately after the switch flips, the inductor refuses to allow its current to change instantaneously. So at that moment, the current in the inductor is still 60 milliamps, but with the voltage at 0, which the capacitor insists on, right? The capacitor doesn't allow its voltage to change instantaneously either. So the inductor refuses to change its current. The capacitor refuses to change its voltage instantaneously. So V out of t is still 0 after the switch flip because the capacitor holds it at 0. But the current in the inductor is also held at 6 milliamperes by the inductor. So the capacitor then must accept the other 60 milliamps that the resistor has to have, because the voltage on the capacitor inductor pair is 0, and the voltage across the resistor suddenly jumped to 12 volts. So that resistor will sink 120 milliamps of current. The inductor refuses to take more than 60, and so the capacitor must have the other 60. And that's fine, but the current going into the capacitor, we know that the current is C d I d, or we know that the current is C dV dt. So if the current is non-zero, that means the voltage on the capacitor starts to increase over time. This 1 microfarad capacitor is a really small capacitor. So the rate of change of the voltage on the capacitor, we know that the current of 60 mA that the capacitor accepts, it must be C dV dt. So this is 1 microfarad times V prime of t, or Vc prime of t. So if we divide the 60 milliamps by 1 microfarad, we would multiply by, okay, so the micro, we get an extra 10 to the third. And so then it's 60 times another 10 to the third. So the rate of change of the voltage on this capacitor is 60,000 volts per second. Meanwhile, the source is only 12 volts. So the capacitor will charge in a fraction of a second. In fact, just about 10 to the minus 4 seconds. In 10 to the minus 4 seconds, this capacitor is going to be at 6 volts. Well, 6 volts is actually not quite enough. It's not done charging quite at 10 to the minus 4 seconds. This this 6.124 is where you're going to be. Well, it's not. I don't want to get too deep into it, but this is going to, the voltage on the capacitor appears to increase to, it's in the vicinity of 6 volts. But what actually happens though is the current in the inductor, of course, now there's a voltage across the inductor, so the capacitor charges really quickly. And so the output voltage at about, t equals 10 to the minus 4, this term is going to be much smaller. This is going to be, e to the minus 0.01. And so the 6.124 volts term here, this leading term, this is the slow term. It takes a very long time for this term to decay. Whereas this term, the e to the minus 9899t, is a much quicker decay. For any given value of t, this e to the minus something is going to be far smaller than this one. At exactly t, these two are equal and they equal 0. The minus 6.124 is very quickly decaying. It's long gone after, after a millisecond even. This term is long gone while this term is still kind of meandering along. So the voltage rises very quickly to about 6, at which point the voltage is enough to cause the inductor to start increasing the amount of current it takes. As the current in the inductor increases, the capacitor then is accepting much less of the current from the resistor. And so, in fact, this capacitor charges up to the point that the resistor's current and the capacitor's current, this actually charges to the point where the capacitor is discharging through the inductor. So there's some amount of current from the source through the resistor that the inductor needs to accept. However, after a point, the capacitor actually begins to discharge through this inductor. The inductor has absorbed enough current that the voltage across it has to decrease, and the capacitor's voltage is beginning to be sapped by the current. So early, the resistor's current splits between the inductor and capacitor. But after the capacitor is charged enough, it actually becomes that the current in the capacitor actually begins to, it starts with current entering the capacitor from the resistor, charging it up. It's not too long before the capacitor is actually charged high enough that the inductor allowing the current through it to increase. Actually, the inductor draws more current than the resistor wants to provide. And so the current from the capacitor actually begins to flow out the top, decreasing the voltage on the capacitor, and the inductor increases its current. And as it does so, the capacitor actually supplies some missing current with the resistor to meet the current request of the inductor under the voltage it has. And so the capacitor begins to discharge through the inductor. So it charges very quickly and then slowly discharges through this inductor as this very large inductor, which is very resistant to a change in current, very slowly saps the voltage off of this capacitor. And so that's why there's this long-tailed term where there's a very quick charge from this capacitor, but the discharge has to be very slow because of this very slow inductor, or very large slow inductor is kind of the idea. So this tiny capacitor charges, bang, but the inductor meanders along very slowly, sapping that charge away. And so this is the reason that it's important to talk about underdamped versus overdamped versus critically damped. Okay, this circuit is overdamped. Um, and so the resistor here is very large, is what happens when you're dealing with an overdamped situation. And in an overdamped situation, the more overdamped it is, the smaller this, or the slower this term becomes. And this slow term means that the discharging process, this the resonance here is being very heavily damped by this resistor. And so the capacitor charges very quickly, but then it has to discharge slowly. And so it's when it's critically damped that both the charging and discharging cycles are both very quick. And so you get this very speedy decay when you're critically damped, whereas when you're overdamped, there is a slow decay and a fast moving term. And so the slow one wins out in a lot of cases. When you are underdamped, it's just there's not enough dissipation. And so there's massive resonance in here, and it's just you get two very long-lived terms in your complex conjugate roots. So if you're overdamped, you get two real roots. One's really small, one's really big. When you're underdamped, you get two really slow complex conjugate roots. And when you're critically damped, that's when everything's all zippy and moving quickly. And so that's where those terms come from, the critically versus over versus under. Okay. So that's the overview. This video is like 50 minutes long, isn't it? Or an hour. Anyway. So that's kind of the idea with these S-domain circuits. And so it's really neat because it allows you to not have to think too hard. You still have to do the partial fractions at the end. So it still has all the complications of Laplace transforms. But at least you're not setting up and solving complicated differential equations and factoring in their initial conditions and trying to remember the particular form, or the form of the particular solution and the form of the homogeneous solution. If you transform the elements, then the circuit analysis part just acts like basic DC stuff. You get an expression and then you just have to do a little bit of partial fractions. But as you saw, there's this shortcut where you sort of plug in the key values of S. One other thing to note as a reminder, if you end up in a critically damped looking situation, where you get two real roots, you're going to get an s plus root squared, or an s minus root, I guess I should say, squared term. If you have a 1 over something squared, you need a 1 over that thing squared term and a 1 over just the thing not squared. So I guess I should be explicit here. So if you have something that looks like, if you have an expression that looks like, 10 over s plus 1 squared times s plus 2. Right? Okay, I wrote s plus 3, so we'll just make it s plus 3. Then what you would have to put on the other side, let me erase this. On the other side, you would get a over s plus 3. You would need b over s plus 1. And you would need a c over s plus 1 squared. Well, when you try to do this, you'll see that the thing where we try to plug in minus 1 doesn't work unless we get s plus 1 out of all of the denominators. Otherwise, we're dividing by 0. So you are forced to multiply through by s plus 1 squared. And so when you do that, you have an s plus 1 on your b. So the a and b disappear. You can only get a by multiplying by s plus 3 and plugging in s equals minus 3. You can get c by multiplying by s plus 1 squared and plugging in s equals minus 1. But there's no shortcut for b. So then you would pick some other value of s for b to get hold of b. And so in this case, I would recommend s equals 0 because it's pretty easy. Or s equals 2 is probably pretty good as well. No, you don't want to do s equals. So I mean s equals minus 2 being right between s plus 1 and s plus 3. Yeah, negative 2 would be my choice. Though 0 is pretty good also. So if I just plug in s equals minus 2 to get hold of b, well, this would become a over, if s is minus 2, this is a over 1. If s is minus 2, then this will become plus b over minus 1. And if s is minus 2, this becomes negative 1 squared, so then this will be plus c over 1. So it's like, okay, so that equals a minus b plus c, which is pretty good. And then on the other side, if we plug in minus 2, this becomes negative 1 squared times 1, and so then this is just equal to 10. After doing the plug-in trick, you'll get something. What would we get? You'd need to know C and A the easy way, and then you would drop those values of C and A in here and solve for B. But that's just a reminder of how you have to vary it in the case of a double root at a particular S value. If you have a triple root, then you get three fractions, one with the power of 1, one with the power of 2, one with the power of 3. And then you'd have to get two extra equations from plugging in nice values of S. Um, there's not always a nice value. Sometimes you just got to pick one and run with it. Um, in the case where nothing's nice, probably your best choices are 0, 1, minus 1, 2, minus 2 in order, if any of them are legal, because of course you might have some of those be the denominator roots. So, but you just pick some S's. So you can, some of them are easy to get if you have multiple roots, some of them are not so easy. But you just punch in some S that is not going to make you divide by 0 and get one of the infinite number of equations that you can construct using the fact that this has to hold for all values of S. Okay, so there's infinitely many systems of equations that have the same answer, which is not a surprise when you really think about it, but the fact that there's an infinite number of linearly independent equations you can get from this setting the two sides equal because there are an infinite number of s's under which they are truly equal. That means you get an infinite number of equations. And any of those equations for different s's are all linearly independent of each other. I believe that's accurate to say. Can you tell I love this stuff? Anyway, if you made it all the way through this part of the video, I hope you're having a wonderful day. And good luck on the final, which I'm sure if you're looking at this video, you are close to your final exam, whether you're in my class or not. So I hope everything's doing well. I hope this clarified some things, even if it ran a little long and went into possibly some things that you already understood already, but I wanted to be very general on this. And so now I need to edit this and upload it. Okay. Have a wonderful day, everybody. Bye bye.